we'll get down to the following. Four equations, sorry. It is M12 over P minus M11 plus 2M22 minus M1 plus 2M22 over P. Four equations, one of those. I won't go through more details of solving them all. I'll give you the solutions. That M11 ends up being square root of 2 e to the 1/4 power. M12 equals M21 to square root of p. And 2 e force power square root of 2. Not nice. The nice name one.
Sorry, I missed where did you get
Basically, took all this, put Q on the other side. So multiply all those matrices and do all the sums. You get this mess. Solve these expressions, so forth. They'll have to equalize out, and you'll get those solutions. I won't go through the 40 details of that. Sorry. But sure, you guys, given enough time and enough paper to do that. Right? So now we have to find the gains. Well, the gain is minus R inverse B transpose times solve for M.
In your lecture, there was no minus before R inverse.
This matters, as I said before. Am I assuming negative feedback or positive feedback in my feedback path? You'll see people do it different ways. What I'm kind of assuming is a minus sign there. Plus sign there. If I want a minus sign there, I'll put a plus sign over there. Make sense for those? And if you read different textbooks, different things, people have their own style for that. In fact, people have their own letters for all these things. A very common one, instead of V, is J as the penalty. All right, so pick a letter, somebody's used it. Okay, so if you read different books, you'll see different symbols. Don't let that throw you. Same stuff. Right, yeah.
What's this method called?
This is a Riccati solution. This is a Riccati equation. It's sort of the opening of what's called optimal control systems. Because optimization, we're trying to minimize or maximize something. That's what we're doing. In this case, it's counting. Right. So if you solve for the K's, put in all of the parts of these things, it ends up being 1 over square root of P, square root of 2 over P to the 1/4 power. So it simply depends on the penalty parameter I had for my eraser for you. Let's look at the new system. So do we know anything right now about closed loop roots? Damping ratio, natural frequency, any of those things? I haven't defined any of those things, but we can find out what they are. signs here, a plus sign down there as well. Okay. This is basically showing this equation, or these sets of equations, where x1 dot is equal to x2. Well, I've integrated here. Whatever s is the integration, right? That's equal to x1 dot. Take x2, backwards on it, that's x2 dot. And x2 dot in this case is u. And u is, oops, p states. Right. So this will be the feedback for x2, which is square root of 2e to the minus 1/4 power. And this is e to the minus 1/2 power. Everybody follow that? Haven't done a lot of block diagrams and such things, but remember, whatever aspect of integration. All right, well, let's look at the equations, state equations for this piece in closed loop form. So now x dot is ax minus b times kx plus whatever the input I have, we've got the other inputs, or that's the same thing we've always had. It doesn't change. The only thing we've done is how have I figured out what my gains are? The only difference we've done. Okay. Well, this is simply in the numbers 0, 1, minus k1 minus k2 times x plus b times whatever inputs I have. I'm not worried about the other input. Let's look at this guy. And if we put in our numbers for this and find the characteristic equation, how do we find characteristic equation?
SI minus A.
SI minus A. The determinant of that. So the characteristic equation is the following. S squared plus square root 2 minus 1/4 s plus c2 minus 1/2 power. Got to turn it off. I apologize. I'm bad. My bad. What's the natural frequency? This is where does the natural frequency show up in the characteristic equation? Second order. Square root of less. Square root of this piece. So let's say this. Where's that? What's this expression equal to? That's 2 zeta omega n, which is square root of 2 over p to the 4th power. Or if you solve for zeta, find it 1 over square root of 2. We didn't choose that. That's what we got. We did not choose the roots on the same, but we can find them on the characteristic equation. Right? Make sense what we do with these things? Fortunately, if I have numbers instead of symbols, we can use MATLAB, and MATLAB solves this in very nicely for us. Piece of cake to do, but understand what you're doing. using that one. Six. The one with the endpoint. Input penalties. These I won't express these views, but we'll just show you what they. I think that first problem we did was that symbol first one in here. And for, I'm going to put in an input penalty in the same form as these others. So we're going to call this H matrix. So this is the input penalty. It says, I want to arrive, in this case, at the origin, and I'm done. Right? And I'm going to penalize how close I get. Right? So if this is trying to put a space probe on a planet or something, and I'm aiming for this particular crater, how close to get to it? That would be perfect. Penalize it. And then I have the path penalty, and it'll be the same form. And I didn't define initial conditions in this. Condition is the same. Okay, in this case, our A matrix, B matrix, all the same things we had before. I let the Q and the R matrix be the same. But I'm going to define this now, input penalty H, in the same form as the quadratic. Right? So this is really at the final condition. Okay, now I want to find the gains for this. Now, the interesting thing is that my gains are going to be functions of play. Because M is going to be a function times the differential equation solves it for him. That's electrical. Look at this Rakai equation.